Everybody. Welcome to Wright Memorial Public Library's Soft Robotics program. I'm Diane Bankson. I'm your host, and I'm one of the librarians at the library. Jack Brown is our leader today, and he's here because he is really interested in robotics in general and soft robotics in particular, and he's really interested in what you can do to make soft robotics with household materials. So I'm going to suggest that you wait for moments to ask questions. If you have a question that you really need answered, please put it in the chat and I will read it to Jack. I think that might be the easiest so we don't interrupt him a whole lot. Also, if you have the bag of supplies from the library, Jack asks that you just keep all the supplies in the bag while he shows you what to do. He wants to show you beginning to end to save you from making mistakes, and also because the press and seal wrap in that bag is a bear to work with. So to not get it all tangled up ahead of time would be really great. So, okay, we are going to go ahead and Jack, you want to take it from here?
Yes, thank you, Diane. And everybody, welcome to my laboratory. I'm excited to share some of the things that I've discovered about soft robotics over the last couple of years. And my biggest hope is that you'll be able to make your own robot grippers and possibly some soft robot muscles, and perhaps share them with Diane at the library, or send a photo of your creation. And I'd love to see them as well. Because that's what we're doing now. First question, why would you want a soft robot gripper rather than a hard gripper? And I want to start just looking at my hand. My hand's pretty soft, and you can see I can grip things with different shapes and sizes. Here I'm gripping an eggshell. And you can imagine I can grip a tomato, or I could grip a tiny little screw, or what have you. But let's take a hard gripper, and I don't have a robot arm here in this lab to show you, but I have a pair of vice grip pliers, and many robot grippers have something similar on their ends. And let's see if we can grip that egg. Oh no. It's been destroyed. And you can see the egg is very sensitive to the amount of pressure. And in order to pick up an egg with something as hard as a metal jaw grip, as opposed to your fairly delicate fingers, you have to have a lot of expensive other additions to the robot. Like, it has to be able to see in great detail, and it has to be able to sense how much pressure it's applying to the egg or the tomato, or imagine a grape or any other kind of object. Now, over the years, since robots have been developed, people have tried to emulate the skills of the human arm and hand. And when you talk about robot arms, you're often comparing it to a human shoulder, elbow, wrist, fingers, and the hand motions. And we need that to be able to pick up different shaped items. And pretty much right away, people figured out that to pick up different shaped items, they often had to design a separate gripper, a separate shape of the gripper on the end of the arm in order to pick things up. Sometimes they were able to use suction cups, with air-powered suction cups if things were flat, and they could press down and pick it up. Sometimes if they were picking up steel, they could use an electromagnet and pick it up and then release it somewhere else. But for the vast majority of items that you might have in a factory or a warehouse or a store that might be manipulated by a robot or assembled by a robot, you had to have a separate gripper for each one. So that's the second reason why people have been interested in developing soft grippers. Now let me show you, before we start building, a couple of samples. Here's the very simplest one that we can build. And I'll show you how to do that in a moment. But what we're going to do is simply withdraw. This is a vacuum powered one, and I'm just going to withdraw the air, and you can see that it takes on a particular shape and forms a grip. And in fact, if I wanted to pick up an egg with this, that would work very well, and it doesn't apply enough force to smoosh it. So that's basically what we call a one-finger gripper. Let's go for a two-finger one. Notice the ingredients are simple. I'm just using a straw in this case, although you could use rubber tubing or plastic tubing. And I'm just going to take the air out again, and you can see that now it could pick up some even more interesting shapes. And you can also see it responds pretty quickly. It's not strong, but it responds quickly. So that's a 2. Now here's one that has 3 really short fingers. And this particular one, I'm using a very small, actually this is a bendy straw, and I'm going to use my lung power and see if it works. I hope it doesn't grab me in the face, but let's see what happens. Now you can also use your syringes on these, but you can see it's simply plastic wrapped around some little cubes stuck to another piece of plastic or paper in the back. So it appears to be pretty simple. Now, let's go one more level of complication. And this one is a bit older, doesn't work so well, but you can see it has 4 fingers. And let's see if it works at all. Okay, we hold it up and we use the syringe on this one. And you can see it, actually, let's do it like this. And you notice how it doesn't move very far, it doesn't collapse very far. And that's because, do it again. Now it's working, and I wonder why. And I'll show you how to diagnose common problems when you assemble them, because this has one of those common problems. It doesn't work as well as it could because of where the tube is located inside the device. Okay, let's review the materials that you're going to have in your kit, and let's start building. Please don't take it out though, okay? And I'm starting with ordinary kitchen wrap called press and seal. Oops, now see what happens? See how I messed that up a little bit? Because I didn't pull it sharply enough up. There we go. And you'll also notice, you see how it sometimes gets tangled up. And you can straighten it out if you're very careful. But I want you to notice that there is a sticky side. If I just touch my finger to this, it sticks to one side, but not the other. And for all the work we're going to be doing, we want to lay this sticky side up on the table before you start assembling. Okay. The other items in the kit are some straws. And if you run out of the ones you have, it doesn't really matter. You can use big milkshake straws. You can use tiny straws. I think this straw was from a McDonald's fast food shopping trip. Doesn't matter. You can, as long as they fit your syringe, or alternately, you can use your own lung power to pull the air out. Now, 2 key concepts that were used to develop these particular devices. One is origami. These basically fold up under different conditions. And if you like origami, you're going to like how to do some of these constructions. And the second is vacuum. And I want to explain using the syringe how this works. If you'll notice that in this particular case, I've got it set on 10. If I put my finger over the end and try to pull on it, if I can pull it to about 30. In other words, I'm making the space 3 times as large and the air pressure is going to be reduced. And as air pressure is reduced, the surrounding atmosphere is still pressing in at over 14 pounds per square inch. And that's why these grippers are going to be as powerful as they are. Now, they're limited by the atmospheric pressure of 14 plus pounds per inch at sea level, but that's enough to pick up small objects. Okay, the other item in your kit is a small cube. And this cube has one side with a piece of white paper on it. To use the cube, and I'll take a piece of plastic here just to show you how to apply it. To use the cube, you use your fingernail to peel off the white paper, and then you decide where you're going to place it. And I'm going to place it about here. And so now I have 3 cubes. And part of the design and part of the skill that you can develop with these is, imagine if you have plastic all around it and you take the air out of that plastic, the atmosphere is going to push in and it's going to cause these to move together until they touch. So the critical design part for you building your gripper, if you want to determine how much it's going to curve, is you determine how far apart these cubes should rest. Now, for the simple ones that we're going to do today, if you look closely, you can see that they're about 1 cube width apart. And the easiest way to do it, and I think to get a better image, I'm going to turn the camera around and face it down so you can see me work a little more easily. So bear with me when I reverse the camera. Well, there we go. Okay, this is your robot construction work tape. Now, the first thing to do is to select the materials that you are going to use as your backing. And you really have 2 choices. You can use a piece of cardstock, piece of paper, which works very well, or you can find a piece of plastic. See, this is translucent. It could be clear plastic. It doesn't really matter. Let me show you over here. When you go to the grocery store, this is a lettuce container that's made out of clear plastic. And your recycling bin is a good resource for different kinds of plastic that you might want to use. If you want your robot to last a long time, the plastic is going to be more durable as a rule than the paper. If the paper gets wet, or if it gets curved too much, once it bends, it doesn't rebound. Once it bends past a certain point, it doesn't rebound, whereas you can bend the plastic and it rebounds every time. The key quality of the material is it springy enough to allow your device, and I want you to watch how it springs back. I'm going to take the air out, and then when I let go, the paper, in this case it's paper, doesn't completely straighten out. And that's because if you'll notice, it's starting to get little folds in it. Whereas the plastic ones tend to be more durable. And here's a plastic one I think you can see. Pulls up, and it pulls out, pulls up, and so forth. And it doesn't get crinkles in it as quickly. So the plastic's going to be more durable, but I'd recommend going ahead and starting with the paper because it's easier to cut. Okay, so let's talk about the shape. Basically, the length of the paper or plastic that you're going to cut out should be long enough to accommodate how many how many cubes you want to have. This one has 5 cubes, and here's a nice one that has 4. So let's make one with 4 to start out with, and I'll just show you the easiest way to do it. And by the way, this thin part on the end is just a support for the straw. It's something that you can use to tape the straw on to keep it straight and to keep it firmly fixed. Okay, so real quickly, I'm going to peel off and I'm going to stick them right here. And of course, you can move them around until you take that paper off. But what I like to do is just space them 1 cube apart. And I do that by taking a cube that hasn't had the paper taken off and slide it in right next to it, like that. Then take another one, slide it in right next to it, like that. Take one as a space. So I'm just using a spacer. They don't have to be equally spaced, but you can experiment with it. But just to get your first one easily done, this is fine. So we're going to just do 4. And now I'm going to take one of my straws. Now here's the key thing, and this is one of the errors. In fact, that's why this one doesn't work so well. When you insert the straw and tape it down, don't have it adjacent to this first cube. Have it spaced at least a 1/4 inch away. And that's so that the air, when you pull the air out of the straw, it has to pull it around the sides of each of these cubes. And that also means that your plastic or paper has to be about 1/8 of an inch or so wider than the cubes. And you can experiment with that, but if it's the same size as the cubes, the air is not going to have room to escape and it won't bend equally all the way across. Okay? So, but before I tape the straw in, I'm going to take my scissors and I'm going to cut the end off just to leave a little tab to seal it, about that much. And then, because we're dealing with plastic, it tends to have sharp corners. I'm going to round these corners off so it doesn't poke a hole. You can see how I rounded them, so it doesn't poke a hole in my press and seal. Okay, now I'm going to take a piece of Scotch tape, not that big, and I'm going to hold my straw in place and just gently wrap the tape around to hold it. And now I can also do a test. You see how I'm just folding it up? And that's how much it should, if everything goes well, it should leave enough space before these hit each other to close about that big. Okay? Now, I've got a piece of shrink wrap ready. I hope this one hasn't been dropped. Now, if you drop these on the floor and they pick up dust, that could be a problem, but let's see what happens. So what you want to do is basically fold it in half, and there's 2 choices. You can either fold it lengthwise, like this, and fold it over, or you can fold it sideways. I generally like to fold it sideways on these simple ones, because that way you're going to have less seams to worry about. See if you can see that. And anyway, I'm going to lay it there. And just stick it down first where I want it, and then fold it over. And first I do the side, then I do the front, and then I do the straw part. Now that's not sealed perfectly well yet, and I haven't trimmed it up, but I can, at this stage, what I want to do is make sure, see these little crinkles? Make sure those crinkles are all flattened out, and they'll reduce the amount of leakage. The main leakage is going to come around the straw and we're going to tape that up to reduce it. But I'm just going to do a test with lung power and see if it works at all. And that's the first step. Okay, that's not too bad for a start. So what I'm going to do is trim it up. And let me show you how to do that. Don't get crazy on your trimming. Leave probably about 1/2 of an inch on the side, because press and seal needs enough of an overlap to make a good seal. And then on the front, I'm going to leave a little more on the front, and I'll show you why in a second. I'm going to fold this over and put a little piece of tape on it just to kind of double check that it's stabilized. Okay, and now here comes the critical part. I'm going to wrap it around this base, and then the tape should overlap where the press and seal hits the straw. See how it's overlapped? You start it here, and you wrap it around so it makes hopefully as airtight seal as possible. Okay, now we're ready for another test. How's that? Now, I think that's about as good as you could expect to get on your first try. The only thing that I might do a little differently, you see how there's a kind of a narrow gap between the side. The only place the air can get through is right along here. And I think I probably should have made it about 1/8 of an inch wider on each side to give myself a little bigger air path. And that's what causes the speed. The more air can bypass each of those cubes, the faster it will both contract and retract. I wonder, let's see if it's strong enough to hold this egg. So it works on an egg. I don't think it would pick up anything too big. And I think it could really stand to use 5 cubes as well. So you can vary the number of cubes. Now, if you don't like it and you want to take it apart, be aware that you're probably not going to be able to reuse the press and seal, but you can reuse the cubes. They can be peeled off. And of course, you can reuse the straw. So before I get more complicated, let's see if there's any questions. Diane, do you want to unmute people, or did we get any questions on chat?
I was muted. There were no questions on chat. Does anyone here have questions? You can just go ahead and speak if you do. Okay, I assume that's all been.
Okay, pretty straightforward on how to do that part of it. Now, let's go back to our little, we'll call this a test facility. Now notice, let's peel these off, and let's see what happens if I move them closer together. Okay, now you'll notice the maximum bend is going to be much smaller, okay? However, and I don't suggest doing this until you've succeeded with the, kind of the standard designs, but there's no reason that these need to be cubes. Can you imagine what would happen if you cut it on the diagonal here, right, from this corner to this corner and this corner to this corner? Even though they were close together at the bottom, they would be able to contract further. So, think of it as your finger if the joints are closer together, you're going to change the kind of flexibility that it has. Now, there is even the possibility, of course, if you have a sufficiently flexible piece of plastic or paper, you can imagine that it could be made to twist. Okay, now it's not going to twist this way, but if I carve them in the right shape, when they compress, they could twist. Now, I don't know how I would use a twisting grip right now, but that you might just think about how you would design those grippers. Now, let's go to the see what's different about the two-fingered model. And the key factor is, again, you probably want to have, I'd say at least 6 or 8. This particular one has 8 cubes. And if you test it, even before taking the air out, you can see there's plenty of room. In fact, I probably could have gotten away with 6 cubes on this that would, completely close. You can see they almost start to overlap. And you can also see that can grip 2 fingers loosely, 3 fingers tightly, but it doesn't close tight enough to pick up a really small object. And remember, the whole point of flexible or soft robotics is to be able to pick up objects of all different sizes and shapes. So ideally, you would want something, and in that way, let's do the 5 one here. You can see it could hold 2 fingers, not quite 3 fingers. It might need 6 to get 3 fingers grip. Okay. And it really wouldn't hold 1 finger because it leaves too big a gap in the middle. But you can control all that by how closely and the shape of the edges of the cubes. Okay, now, if I want to build 3, notice I've just taken basically a circular piece of plastic and taken a protractor and divided the circle into 3 equal sections and drew the lines accordingly and cut it out. That's pretty straightforward. And this one, I only used 2 cubes per arm. And I knew that wasn't going to make it crunch up too much, but let's test it again. That's probably enough to hold our egg. Let's see. Yeah, that's about an egg-shaped or an egg-sized gripper. Now, we'll come back to different ways to test the basic grippers, but before we get too late, I want to show you how to make the vacuum-powered muscles, okay? And robot muscles have developed over a long period of time, and people are always trying to emulate human muscles. And if you'll notice, if you contract your bicep, let's see if I can, if you contract your bicep, you notice how it expands in diameter. And at some point, if your muscles are too big, you can't move your arm as far as you could otherwise because the muscle actually gets in the way. And the nice thing about these vacuum muscles is that when they contract, they just contract in one dimension. And I'm going to hold this end and see if I can pull it. Let's hold it out here. Let's do it with a syringe at a distance. It's about 4 inches long when it starts, and it contracts down to about 1 inch. But you'll notice, because all that's happening is the air is being removed. Let's hold it at an angle here. Now let's put it next to the ruler so you can see. This is a 6-inch roller. And it's contracting about 3 inches, okay? Now I haven't trimmed up all the edges, which, would make it more compact. But let's see how to make those. Again, it works by the same principle. This plastic or shrink wrap that's stretched over these curved folds, when there's normal air pressure on both sides, it's supported between these shapes. When I pull the air out, when I reduce the pressure inside, you see what happens. Whoops. That plastic starts to collapse. And then when I release the pressure, it flows back in and it expands out. Now let's show you how that might work if you have kind of your classic robot arm elbow. In this case, it's actually a Romeo's pizza box, which makes great cardboard robot arms for experimentation. But if I hook my syringe to that, let's put it so everybody could see, and withdraw the air, whoops, excuse me. When the muscle contracts, it pulls the arm in. Now for that to work, there's the pivot. In other words, this would be equivalent if you're thinking of a human elbow. Here's my elbow. That's that little bolt. And in fact, this is your bicep, and the bicep is connected pretty close to the elbow, and it's connected to the upper arm. And when it contracts, it pulls the arm up. But it can do it in a very smooth and pretty sensitive way, just like the human muscle. Or alternatively, we could use an electric motor, or we could use a hydraulic device with water or oil to use positive pressure as opposed to vacuum. And we'll talk a little bit about the advantages and disadvantages of using positive pressure once we finish building this muscle. Okay, let's see how to do it. The first step is simply to find a piece of material. And in this case, I'm going to use cardstock instead of plastic. I'm not going to take the time to measure it, but I would advise when you build your first one, try to make them equal folds. And if you were doing origami, we would call this a mountain fold, where we're going to fold it one way, and then we're going to fold it the other direction, same width. And we're going to keep doing that. We're going to fold it back and forth, back and forth. And this is also called a Z-fold, okay? And now we have a device that we could place a straw, just like we had before, on one side, okay? And we could wrap it in shrink wrap. Now, there's one additional thing you can do to make these more efficient. It will work without it, but I recommend, all except the end ones, you can punch a little hole with a hole punch, or if you're careful, you could even cut a hole or have your parents help cut a hole in it. But cut a small hole, and the purpose for that is to allow the air, just like the gap around our foam cubes. I guess we need a hole here. Okay. Now, when the straw is pulling on it, when the air pulls through the straw, it can go directly through. The only place it can't go through is around the shrink wrap. So let's see if, and we don't need our foam cubes for this. So let's go ahead and do it. Just because it's a little easier, I'm going to tape this straw loosely here so I don't keep dropping it. It was not very efficient, was it? Okay, so we have the straw roughly on there. And I'm going to grab a piece of shrink wrap. And again, remember, you want to be putting that shrink wrap sticky side up. Okay. And I'm going to start it about here. Now it looks like, notice, this shrink wrap is not going to be quite long enough that dimension. I hope it's long enough in this dimension. Here we go. That's probably just long enough. Let's see what happens. Now notice I could have put it over sideways, but I just wanted to show you the alternate way of doing it. Okay. Now, even though it isn't sealed yet, let's do a quick test and see if we are, yeah. Even without sealing it, it looks like it's going to work. So I'm going to go ahead and cut it off, and then we'll build another one with the other sealing method. Now notice, because it's folded over here, we don't have to worry about leakage out the front. What we do kind of have to worry about leakage on the sides. And there's a couple ways of handling that. And we kind of taper it back toward the straw because we're going to tape that down. Okay, so what I'm going to first do is just wrap these around like this. Now you don't have to use Scotch tape. In fact, the stronger the tape you have, probably the better. But Scotch is easiest to use. So I wrap that around, trying to make it as smooth and airtight as possible. And let's do another test. Oh, by the way, never press air into the muscles or grippers, because that tends to open the seams up, and then you have to reseal them. If you have to release it, well, first I'm going to take the air out. Whoa, that worked really well. Now notice I took the air out, and you see how it's not expanding very rapidly? Well, if you have a weight on the end, it doesn't really matter, because the weight is what's going to pull it out. But watch. Okay. In fact, let's test it with a weight. I think I've got something right here. I'm just going to take a plastic clamp and put it on the end like this. I'll lay it on the table so you can see it. Okay, so it'll drag it, and I wonder if it'll pick it up. Let's hold it up. Let's get this up here a little bit. Okay. Now notice when I take it off, when I need to push the syringe back in, I take it off the end. Now you hear that sound? It's leaking a little bit, and that's because I forgot and pushed the syringe in directly. So let's go ahead and I'll show you how to seal it so it's not going to leak as much. You take your thumb and forefinger on each side and just smush it together so it's nice and solid. And then we're going to peel over the end, because that doesn't have to move very much. And we're going to tape it. Okay. And in fact, we can probably put a little tape on these right next to the straw, because that doesn't have to bend that much. You don't want to put so much tape that you reduce the ability for it to collapse when the air is removed. Okay, now let's try it again. Now again, whenever you have to push the syringe in, make sure it's not connected to the end of your straw or rubber tube. Now, there we go. You see when I let it go, it starts to spring back. If I just pull it back, that'll be fine, as the weight would be on it. Pull it back, pull it back. Now, I can kind of tell, you see, if you look up close, you see how that plastic is really pulled deep in between the folds? And this particular paper is not really springy enough to help it move back by its own, or to help keep the air from totally collapse, the air pressure from totally collapsing. So what you might want to do is use some of this firmer plastic. And let me show you how that folds. Here's some really firm plastic. It's really just like a spring, okay? And again, you want to punch a few holes in it to help it along. But let's try this plastic and see how it folds. You can also control the amount of stretch by making the folds shorter. A big, long fold is going to cause the air pressure to totally collapse the plastic, but it tends to do it once and then it doesn't rebound. So you really want to do pretty short folds. There we go. And the way you can test it is you want to see, now this particular plastic, it's pretty springy. I think this would be okay. Okay, now does everybody remember how we prep it before we take care of it? Step one is to take the sharp edges off. Okay. And step two is we want to thin the last one out that the straw is going to rest on. So it's going to be easier to seal. Okay. And step three is going to be to cut or punch. You don't do the first one, it's the second one. So this is going to need 4 holes. These little tabs don't always fall off. Okay, so we've got so we're hoping that at full length, it's about 2 inches long and it's going to contract about 1 inch. So let's tear off a clean sheet of wrap. Let me get this. Okay, I'm making quite a mess here. Which side is up? Sticky side up, exactly. And then we're going to find our, hopefully we're going to find our piece that I just laid down here. There it is. We're going to lay it like this. And in this case, I'm going to fold it sideways rather than endwise and see if that works any better.
Jack, can you move it up just a little bit? We can't quite see.
Oh, yes. Thank you.
There was also a couple questions.
Sure. Go ahead. There we go.
Is could you use saran wrap?
Yes, you can. Great question. It's a little more finicky about sealing. You know, there's a reason that Press and Seal, I think, outsells saran wrap, but it will work. And I've used it successfully on a number of the muscles and grippers. You just really have to work on, using your thumbs and fingers to smooth it together, and you may have to reinforce the seams with tape. I would certainly recommend I'll tell you what, I'm going to actually cut off this straw so I can use the same size straw. I'm going to put it in here. Now, notice the straw, it will actually stick to the straw, so I don't need to tape the straw down absolutely. That's just for convenience. And this way I'm doing the horizontal fold. Can you see that?
Yeah, we can see it now. There was one more question for
Yes.
you. This one, it's from Stephen. If you put cubes and a straw on both sides of the cardstock, so there would be 2 straws, cubes on each side, would it bend in different ways if you blew on each straw?
Let me see if I understand it. In other words, here's a cardstock, and you have one like this and one like this, but perhaps offset.
I'm not sure about it offset, but yeah, I probably would.
If they're symmetrical, it's not going to bend because the air pressure reduction on the top would be equal to the air pressure reduction on the bottom. Okay. But if you did it, that's an excellent question. If you did it like this, okay, you would have a big gap where the outside air pressure would, when the air is a vacuum inside, it's going to press it down here, which is going to cause these to go up. Now it's still, because you have the counter pressure would be on this side. It depends on which side has the biggest area. In other words, if there was more area of plastic on each side of this than there was in the middle, it would bend in that direction. But, that's one I'm going to have to experiment with, but I would think it would be more interesting. That kind of gets along to the twisting idea. If you had your cardstock, and let me just cut one out real quickly with a pair of scissors. Let's imagine that you had it now. If you place these along here, let's just get this out of the way. You can kind of anticipate what's going to happen just by laying them on here and not having to use your stickies up. And you put your straw here. This one is going to bend up this way. This one is this way, and this one is this way. So it definitely would take a curve shape on the vertical side, but it wouldn't compress in this direction. So that's another way, you could do it. But the part that I think your participant was asking about is, well, what if you had a whole series of these on each side, but maybe you change the spacing on the top and the bottom? I'm not sure it would be a gripper, but it might do some interesting things when you took the air out. So we'll move on. Is there a follow-up to that question?
No, there isn't. Sounds like Stephen's going to have to try that one for himself.
I think it'd be exciting to see what happens. And I think the most important part of this whole exercise is don't feel you have to the only reason to replicate what I'm doing here is to get the technique of how to manage the press and seal or saran wrap or whatever you're using. Now, there's another material you can also use, and that is heat shrink or heat seal wrap. It's also used in kitchens to seal leftover food and so forth. And in fact, the original Harvard Research Group study where I got this idea used that kind of seal, and they just used an iron. or the actual pressing, a heated piece of metal, basically, and that seals it. The problem is that for doing it with younger students, I didn't want to mess around with the heat. So I've tested it. It does work, but it's a little trickier if you have younger participants. I say that would be probably high school age and up. Okay, let's test this and see how it works. Now you can see that it's really pulling my hand. You can't feel how strong it is, but I could hang probably 100-gram weight on that and it would pick it up. See, it's picking my hand up. Now, even though it's only moving an inch or so, by the lever effect, as you can see here, depending on where you hook it up to your rotating arm, you can have more or less movement on the end. So if you put it out here, you have less. If you put it really close, you have less power, but a greater range of motion. Okay, so that's the simple muscle. Now the question is, how do you attach it to anything? And here you've got another option. Now you can actually use your hole punch, and because this is self-sealing, I hope that I didn't. There we go. You see, I punched a hole all the way through everything. And now I can take a wire, for example, and here's one that I've already assembled. I can take a wire or a paper clip, stick it through there, and now I've got a mechanism to attach the muscle to another device for motion. Now, the last thing on that is, let's imagine that you built a cardboard robot arm, okay? And if you're going to do it, I recommend using more than one layer of cardboard, but in any case, you still don't have a gripper on the arm. All the arm can do is knock stuff over, okay? It can't pick things up. So the question is, what if you put and you can imagine just taping it in place or using some epoxy glue and, firmly attaching it on here. Now, the question is, how do you get the air? You're not going to suck on the straw while the whole thing is moving, and you're not going to have a syringe attached way up here and another syringe down here. Well, that's when you have the options of using flexible tubing. And you can see that many of the versions have some kind of flexible tubing. It can either be rubber, and here's an example of some soft rubber tubing, a fairly large diameter. And here's an example of a very tiny muscle attached to a very small diameter tubing. And I think this is called taken from fish tanks. So if you go to an aquarium supply store, they're going to have this kind of tubing. Now, the other problem is, how can you turn the pressure on and off remotely? If you're going to have a robot, obviously you want it controlled by something other than you pulling syringes in and out all the time. And maybe you'd like to have it controlled by a little microcontroller like an Arduino, a little $10 computer. And to do that, you're going to have some valves and switching. And this is just a little plumbing T-fixture that you can use to supply either vacuum or pressure from different angles. You can buy small pumps, small vacuum pumps, probably starting around $20 would be sufficient to get, a low vacuum device if you want to move beyond the syringes. Now, before we only have about 5 minutes, I wanted to show you one issue with positive pressure. And let's clear our mess off a little bit. I'm going to put this here. And this is another type of air-powered muscle, but in this case, it is not powered by vacuum, but it's powered by pressure. And so if I hang a weight off this end, well, let's do it this way. Use my handy weight. Okay. And I have this little child-size air pump. And you can see kind of what's happening. It's just like, now you see how it's getting, did you hear that? Just before it burst, it was pulling it up and the muscle was expanding. This is a particular kind of fabric that only stretches one way. It doesn't stretch vertically. It's called one-way stretch fabric, but it's very stretchy in this dimension. And it simply has, you can see by the edge, an ordinary balloon in it. And I think you can see the problem with positive pressure devices. One, when they burst, they scare you, okay? And if this was a powerful one with really high pressure, it can be dangerous. It could, burst the outer covering and throw, particles all over the place. And that's a really serious problem if you want your robots to be able to work safely alongside humans. In other words, if you want your robot to be your assistant, if something goes wrong, you don't want it to hurt you. You want it soft so that if it bumps into you, it doesn't hurt. But you don't necessarily want it powered by positive air pressure if, in order to get the power needed, the pressure is so high that there's a risk of the muscle itself or the gripper bursting and causing damage. Okay, any questions on that? Any questions on that point? Let me go back to video where I can see myself. There we go. So how are we doing?
At this point, I don't have any questions that are in the chat. Does anybody else have questions? I did explain just now in the Q&A part that everybody is on their own for the building now that you've shown them. This is being recorded, and I'll send everybody the link and you'll be able to watch it again if there's certain parts you forgot.
I will also, if people encounter questions or if they have, creative questions like the one about putting the cubes on opposite sides, not only would I be interested in seeing the, photos of what you come up with, but if you have questions, I'd be happy to answer them via email. And I think, Diane, you have my email address, of course. And so, if that's not too big an imposition, I'd be happy to moderate those questions, remotely. Okay, so everybody who signed up today will get a link to this recording once it's up, as well as Jack's email. If you have any other questions. Okay, well, oh, did someone just say something? I heard. I think. No, I don't think so. And also, if you look at the handout, you'll notice there's a reference to the article that originally gave me the idea to develop this. And if you want to see the actual engineering and some other applications for these devices, it's a pretty technical article, but I think you might find it interesting. So follow that link and check it out. Great. Okay. All right. Well, thank you so much, Jack. I learned so much. I learned a lot today, and I hope everybody else did too. Well, thank you all for participating, and I look forward to seeing some exciting gripper developments in the future. Maybe you'll give me some ideas for additional workshops. Okay. Great. So thank you very much. Thank you. Bye, everybody. Bye-bye.
Bye.